change. So today I'm gonna say a few things about estimating the mean of a random vector. So, and this is, as Nikita mentioned, this is joint work with Shahar. So the did you guys? I changed slides, but I don't see it on the.
No, we don't. We don't see the slides.
I don't see it. No.
Let's try to share again.
Okay, let me try to share again. Stop share. And now I do share. Share. I have to go here. Here. Yeah. Can you see it now?
Yes.
Okay. So. The problem I'm going to talk about today is that we have n independent random variables that have a common mean, and these are independent, identically distributed random variables. So this is really the cleanest setup, maybe the most classical statistical problem. And in the first half of the talk, I'm going to talk about the case when these are actually real valued random variables. So the main point of the talk is the case, the multivariate case, when these are real random vectors. But as a preparation, I'm gonna assume that x1, xn, these are IID real random variables. Okay, so of course anybody can say that okay, if you want to estimate the mean, then of course we just take the empirical average, and that's gonna be the best estimator. And in a sense, this is true. In the old days of statistics, people were mostly interested in, I mean, how do you measure the quality of an estimator? In the old days, people were interested in the mean squared error or other types of risk measures, but it was always some kind of an expected risk measure. And if you take, if for example, if you consider the mean squared error, then really the best thing you can do is to take the empirical mean, okay? Because the expected the mean square error. Well, if we assume, and I will assume this throughout the talk, and I will explain a little bit more why, that if the x's have a finite variance, then the mean square error of the empirical mean is sigma squared divided by n, and that's true, and you cannot do anything better, even if the data are Gaussian. Okay? Somehow the problem becomes much richer if what we are interested in is not expected mean squared error, but rather bounds that hold in high probability. Okay? And then somehow the problem becomes much more interesting. And when I started working on this, it was really surprising to me how many things are still open and how many things one can say about this. Okay. So as I will explain later, I will always assume that the x has a finite variance. That this is not a strong assumption. Some of the things can be that I'm going to say can be made can be generalized beyond this case. But if you don't assume anything, then all we know is that as the expectation exists, then there's nothing we can say about the speed of convergence. Okay? Because no matter what estimator you give me, I can always find a distribution such that for that estimator, the error will be large, no matter how large n is. So we can, the law of large numbers holds, but if you want anything non-asymptotic, then we are dead. So, but if we assume the finite variance, then for example, we have the central limit theorem that says something of this. So this is, I formulate now the central limit theorem in a form of an inequality, which is not the exact statement, but essentially what the central limit theorem says is that square root of n times the error behaves like a Gaussian random variable, and in particular, Gaussian random variables have this type of tail behavior. Okay, so the probability that this is bigger than sigma times root log 1 over delta is smaller than delta. Okay, so that's what the central limit theorem says. But of course, the problem is that this is an asymptotic statement. So again, wouldn't it be nice to have non-asymptotic inequalities of this form? Okay? And this is possible if we are willing to assume more about this. If we're willing to assume that the distribution is sub-Gaussian. Okay? By sub-Gaussian, I mean that the moment generating function of the x's is bounded by the moment generating function of a normal random variable with the same variance. Then we have a non-asymptotic version of the central limit theorem. So this is true for every n that with probability 1 minus delta, the error of the empirical mean is bounded by sigma times square root of log 1 over delta divided by n. And I'm not going to pay too much attention to the constants, but here, of course, these are the best constants possible in this case. Okay, so this is what I will call a sub-Gaussian inequality. Okay, if we have something that holds with probability at least 1 minus delta, and the bound is of the form sigma divided by root n times square root of log 1 over delta. Okay. All right. Now, if we don't have the sub-Gaussian assumption, then we can still say something. So Chebyshev's inequality holds whenever the variance is finite. And then what we can say is that with probability at least 1 minus delta, the error is bounded by sigma over square root of n. So that's fine. That's what we had in the sub-Gaussian inequality. But the dependence on delta now is exponentially worse, right? Remember, we had square root of log 1 over delta, and here we have 1 over root delta, which is much, much worse. And then this is important, especially if we want something, you know, in data science or machine learning or whatever. What we usually are not interested in estimating one mean, but millions and millions of means at the same time. So if you want to use the union bound, then you better have something that's logarithmic here, okay? Because otherwise we are completely dead. Okay, so this is a serious issue, and it's easy to show that that if we don't assume anything more than the second moment, then for the empirical mean you cannot do better than this. Okay, so there's a lower bound that matches Chebyshev's inequality, and that's it. Okay, so that's the end of the story. If we insist on the empirical mean. Okay, now, but what if now we can use some other estimators? So what if the empirical mean is not the best? And this is kind of a surprise. To me, it came as a big surprise that we basically don't have to pay any price for not having sub-Gaussian tails in the assumptions. So there exist estimators that have a sub-Gaussian performance no matter what, under the only condition that the second moment exists. Okay, so for me in this talk, an estimator is just a measurable function of the data. Okay, so often I'm not going to be concerned about computation, though I will make some remarks about computation. But to me, an estimator is now, we are presented with the data, and I can take any function of it and output that function. And what I want is that value function should be close to the real mean with high probability. Okay. So one of these conceptually very clever but very simple estimator is called the median of means estimator. That has become really fashionable in the last few years, but it's been around for a long time, kind of hidden in the literature. So several smart people came up with the same idea. I think the earliest is probably Nemirovsky and Yudin, but then in this paper of Jerome Valiant and Bazirani, it comes up in this other paper of Alon Matias and Szegedi. These are papers that were focusing on other things, but they just needed a good mean estimator for some other reason. Okay, so here's the idea. We take our data that has n points, and numbers and random variables, and we form blocks of size m. Okay, so m is the block size. Okay, now within each block we compute the empirical mean. Okay? And now we just take the median of that. So this is, it's called the median of means because we take small chunks of the data. These are random chunks. Okay, so now we don't order the data first. We just take the random ordering. Compute the mean and take the median. So the median of means estimator. And here's what this estimator does. If the block size is chosen appropriately, so in other words, if the number of blocks is something like log 1 over delta, then we have this beautiful sub-Gaussian estimator. Okay? Then with probability 1 minus delta, the median of means estimator has an error that's bounded by sigma divided by root n times log 1 over delta. So this is exactly what we were after. Okay? As I said, I'm not interested in optimizing the constants. One can do a little bit better than this. Okay, so let me show you the proof because it's essentially trivial. So this is the proof, right? So because of Chebyshev's inequality, within each block, remember has m data points. So the probability that with probability at least 75%, within any fixed block, the estimator is within this distance of the true mean. Okay, but now you see, if here's the true mean, and here's our median of means estimator, if this distance is large, then it means that at least half of the averages, block averages, are also far away. Okay. So if distance was less than this quantity here, then it would mean that half of the block averages are also more than this distance away. Okay. But the number of points that are that far, that's just a binomial, right? With success probability at most 1/4, right? So the probability that half of them are this strong, well, that is e to the minus k, and k is log 1 over delta, so that's how the delta comes in. Okay, so this is a completely trivial proof. It's just a nice, clever idea, and we have this wonderful sub-Gaussian inequality that we get completely for free, and we don't need anything anything special about the distribution. Now, a disadvantage of this method is that, as you see, the number of blocks has to depend on delta, right? So you have to tell me what's the probability of error that you're willing to live with, and then I'm gonna give you an estimator. If you want a smaller probability error, then I have to give you a different estimator. Okay? And one can prove that this is actually necessary. So there are. I'm not going to go into that, but the fact that the parameter depends on the required confidence level, that's inevitable in a certain sense. So unless we are willing to assume something else about the distribution. Okay. Now another nice thing about the median of means estimator is that it also works if the variance is infinite. Okay. So for example, if instead of finite second moment, we have a finite 1 plus alpha moment for some alpha that's less than 1, then we still have this kind of performance. If alpha equals 1, if alpha equals 1, then this is exactly what we had before. If alpha is smaller, then we have a slower rate of convergence. Okay, but this is actually optimum, so it's very easy to prove. I'm not going to work out the proof that's written actually here, but you can very easily see that this is the best one can do. Okay, in the sense that for any mean estimator has to have, for any mean estimator there exists a distribution whose 1 plus alpha moment equals m, and whose error is exactly what we had in the previous slide, well, up to this constant 8 here. Okay, so. So this also kind of shows why assuming the second moment is somehow a special, is a good assumption in a sense, right? Because what this lower bound says is that if we want to have a rate of convergence that's 1 over square root of n, then you have to have a second moment. If you don't have it, if we have something only, if we have something weaker, then we have to pay for it in the rate of convergence. Okay? But as soon as we have a second moment, we have actually a sub-Gaussian error, and sub-Gaussian is the best you can hope for, right? So if you want an estimator that is, you see, for Gaussian data, the best you can do is the sub-Gaussian estimator. Okay? So and we get that for free as soon as the variance exists. If the variance doesn't exist, then we are behind in a strong sense, even in the rate of convergence. Okay? So by having a second moment, we win a lot. Okay, so this is what I just explained. Now, still in one dimension, I'm gonna mention now another estimator, which is equally or even more natural than the median of means estimator. And this is the trimmed mean estimator. This goes way back to the classical era of robust statistics, and this is the so-called trimmed mean estimator. And this is what every practitioner, naive practitioner, would do, right? So if you have data here, and you suspect that you might have heavy tails, then you say, okay, let's just forget these outliers. These are outliers. We just forget them and take the empirical average of whatever is in the bulk. Okay, so this is the trimmed mean estimator. It's a really simple bound, but surprisingly, this beautiful property that it is actually, it does have a sub-Gaussian property if the level of trimming is well chosen. This hasn't been proven until very recently. So this paper has never been published, well, or it's never been written, but Roberto Oliveira told me the proof. So Oliveira and Orenstein, they proved that if the number of points here that we trim on both sides is about log 1 over delta, then we have a sub-Gaussian property. Okay, so let me explain you why this is true, and I will explain it in a little bit more complicated estimator, but the proof is simpler for this one. Okay, so this is a two-step estimator, and what we do is that we divide the data into two halves. Okay, so x1 xn is one half, and y1 yn another half. So we have two NIID data. I just denote them differently so that we know that they're from different stages. They come in different stages. So so in the first step, what we do is that I look at the epsilon quantile, empirical epsilon and 1 minus epsilon quantile of the second half of the data. Okay, so this is the epsilon nth smallest yi, and this is the this is the epsilon nth largest yi. So these are the two empirical quantiles, alpha and beta, and now I just consider this squashing function. Okay, and we right where alpha and beta are these empirical quantiles that were determined from the second part of the data, and which I just take the empirical average of all the data that are in between here and here. We just take we just replace everybody by alpha, and here everybody by beta. Okay, so it's just kind of a squished estimator. Okay. All right. Here's the performance. Again, very similar to the previous one. It's a sub-Gaussian performance. If epsilon, sorry, n epsilon, so the number of points that are number of points that are squished somehow in the left and on the right is log 1 over delta, then this estimator has a sub-Gaussian error, exactly the same kind as before. Okay. Once again, the estimator, of course, depends on delta, the probability of error, because That's where we do this this thresholding. Okay. Okay. So here's the proof. It's a little bit longer, but it will fit in 2 slides. Okay. So first of all, by Bernstein's inequality, it's very easy to see that that the empirical quantiles are correct up to a constant factor in this sense. Okay. So the epsilon is between the epsilon half true quantile and the 2 epsilon true quantile. Okay, so I didn't say that Q sub epsilon is the epsilon quantile of the distribution. Okay, so both alpha and beta are correct in this sense with this probability, right? Remember that epsilon is chosen such that this probability is now smaller than delta. Okay. And now we can decompose the error. So this is our estimator. This is a true mean. So I just take the expectation of this thresholding function, and the second part is our estimator minus its expectation. Okay. So the estimator minus its expectation. This is just an IID average. So we can handle it again by Bernstein's inequality, and it will give the right thing. Okay. So I'm not gonna deal with this. This is just a simple concentration inequality for averages of independent random variables. So let's look at the bias. Okay. So the difference between the expectation and the true mean. Okay. So the expected value of the discretion function for the true mean. Remember, discretion function only differs from the identity function when x is either less than alpha or it's greater than beta. Okay, so these are the two contributions from the 2 extremes, right? This is from the smallest from on the left side, and this is on the right side. Okay. Now, because of the because we know that alpha is a good estimator with high probability, I can replace this alpha by Q2 epsilon, and here beta by Q1 minus epsilon. So let's look at now just this term, right? The other term is exactly the same. So so the expected value of x minus this quantile times the indicator that x is greater than that quantile. Well, let's center. So I just add and subtract mu here, and then we have these 2 terms, right? X minus mu times this indicator and this other term here times the indicator, but this other term is a constant, so there's just this probability. This probability equals 2 epsilon, right? Because by the definition of the quantile. And here I can upper bound this by Cauchy-Schwarz. Okay, so Cauchy-Schwarz is the only inequality we use here. And so what we get here is sigma times square root of epsilon, and here we get epsilon times. And now this is the difference between the quantile and mu, but that follows from Chebyshev's inequality that's bounded by sigma over 2 root 2 epsilon. So we get what we want. Okay. Right. So even if you didn't get all the details, you can very simply reconstruct this. There's nothing fancy here. We use 1 Cauchy-Schwarz and 1 Chebyshev, and that's all. Okay. So it's a really simple proof. Okay. All right. Should I ask if there are questions or? Okay, let me know if there are
nothing at the moment. Yeah.
Okay. Okay, great. So a really nice property of the trim mean estimator is that it's robust under adversarial contamination. So what does adversarial contamination mean? It means that that we can have an attacker, an adversary, who can look at the data first. The adversary knows exactly what we're doing. The adversary knows the algorithm that we will use. And the adversary can inspect the data, and he has a budget to change eta times n points any way he or she likes. Okay? Trying to work against us, all right? So now the question is, what's the price we have to pay for this? And the beauty of the trim mean estimator is that it is optimal in the sense that if we now choose the trimming level as function of eta, right? So remember the trimming level, this epsilon before, when we didn't have a contamination, was just log 1 over delta divided by n. Now, if eta is smaller than that, then we don't have to do anything. If eta is larger than that, then we will just choose epsilon to be a constant times eta. Okay? And then we can go through the closure, and you will see very simply that basically everything goes through. And what you get is that with probability at least 1 minus delta, the error is bounded by what we had before plus sigma times square root of eta. Okay, so the price we have to pay for this adversarial contamination is just sigma times square root of eta. And one can show that this is the best one can do for any estimator, right? If we don't assume anything. So if the distribution has nice smaller tails, then one can improve the square root of eta. So for example, if you have higher moments, then the square root of eta becomes eta to some other power. Okay, and you can go down up to about eta. Okay, so in the extreme case, when the distribution is sub-Gaussian, then we can get eta times square root of log 1 over eta. Okay, and this is all necessary. Okay. And as I said, the trim mean just works. We don't have to do anything, and then the analysis is also simple. We don't have to do anything. The median of means is not robust under adversarial contamination, not to this optimal level. Okay, so in this sense, trim mean is better.
And I have a quick question. In the median of means, does the adversary know which groups are being made, or no? Or can the groups be made randomly after the adversary picks the data? No, we should be able. No, actually, as I said, the median of means is not robust, but that's a good point. In principle, it knows that the groups. Yes, it's allowed to know. It's interesting. Yeah. That's a good question. Maybe you can do a little bit better if you can randomize afterwards. That's a good question. Yes, I know. Okay, so now I come to the main topic of the talk, which is estimation of the mean of a random vector. So now we are exactly in the same setup. We have IID observations, but now of a d-dimensional vector x. We assume that the mean exists. Of course, it's mu. So it's now a vector, and I will assume that the covariance matrix exists. So again, and I don't want to assume anything else. Okay. So, the question is, can we now estimate mu such that we have a sub-Gaussian performance? Okay. But of course, now the question is, what is sub-Gaussian? What does it mean that an estimator is sub-Gaussian? In one dimension, that was very clear. Well, it's also kind of clear in high dimensions, because we can just look at what happens if x is Gaussian, multivariate Gaussian, and if we take the empirical mean, which in the Gaussian case, the empirical mean is the best you can do. So, and this is very easy to analyze, because you see this is itself now a Gaussian random vector. So, the expected value of the squared norm is just the trace of the covariance matrix divided by n. Okay, so this is just this first term here is just bounds the expectation of this, and the second term comes from random fluctuations. You see, this is now a Gaussian vector, right? This is a Lipschitz function of a Gaussian vector, so we can use Gaussian concentration inequality, and what comes out is that now this depends on the operator norm of the covariance matrix. Okay, so the Frobenius norm comes up in the first term. This is sometimes called the strong term, and in the weak term that depends on delta, it's only the operator. Okay, so there can of course be a big difference between the trace and the largest eigenvalue of the covariance matrix. Okay, so this is what I will call sub-Gaussian. Okay, sub-Gaussian performance when the Euclidean norm of the difference between the estimator and the mean is bounded by the maximum or sum of these two terms. The one is proportional to the square root of the trace of the covariance matrix divided by n, and the other is proportional to the largest eigenvalue times log 1 over delta divided by n. Okay, so question is, can one construct a mean estimator that has this performance? Okay, so let's look at some obvious ideas. Well, an easy idea is to try to generalize. Okay, so we can again form blocks of the data. We can compute the empirical mean. So now we get, if we have k blocks, we have now these k vectors, and now we should take the median of this. But what's a multivariate median? Well, there are many notions of multivariate medians. We can take the coordinate-wise median. We can take the so-called geometric median, which is the point that minimizes the sum of the Euclidean distances to these centers. Another interesting notion of a median is we can look at the smallest ball, the center of the smallest ball that contains at least half of the data points. Okay, that's another generalization of the notion of the median. There's the famous Tukey median, and so on. Okay, so there are many different notions, and I will introduce a new notion here. Okay, all right. So let's look at what the simplest notions give us. So the coordinate-wise median gives us already something interesting, right? We can just use the previous result with the union bound, and then we will pay a price for the dimension here. So right, because we have the dimensions. So this doesn't look too bad, but we can do better. Okay, so this is not ideal. First of all, you see, if I go back here, you see this this performance bound. This bound here is dimension free. This is an infinite dimensional statement. Okay? In fact, this is true also in Hilbert spaces. I don't want to talk about infinite dimensional spaces, but here, this whole thing just works. You can do median of means. Okay, and as long as this trace is finite, we do have this bound. So it would be nice not to pay for the dimension explicitly. Also, in this other bound, this trace term is multiplied by this log 1 over delta term, and that's not what we want. Okay? We would like the trace term to be separate, and then the log 1 over delta to be multiplied by the largest eigenvalue of the covariance matrix. Now, if you look at the smallest ball median, then it's really easy to show that this is already an infinite dimension-free statement. Okay, so the D disappears here, but this is still not quite sub-Gaussian because we would like this term to be separated from the log 1 over delta. Okay. I put the proof here, but let me skip it. It's really simple. It's really simple. You can. It's a little exercise for you to prove that the center of the ball that the center of the smallest ball that contains at least half of the centers of the block centers is it satisfies this. Okay, it's really simple. The multivariate median of the geometric median of means that computes again in each block you compute the empirical mean, and now you minimize this. This also satisfies this kind of pseudo sub-Gaussian bound, and this was proved by Stas Minsker a few years ago. So this is really nice. First of all, this is computationally nice. This is a nice convex optimization problem. People in computational geometry has looked at it very thoroughly. This can be solved essentially in linear time. So this is really nice. But again, this is not quite a sub-Gaussian bound. Okay. All right. So let me show you how one can construct an estimator that achieves this sub-Gaussian inequality. Okay, and this is what we call the median of means tournament. Okay. So what's the mean? You can think about the mean as the value of this x that minimizes this function. Okay, the mean is just the value x that minimizes the expected squared distance to this random variable. Okay, so if you think about the mean like this, then we can look at candidate estimators A and B. Now we can is better. Okay? Which function? This is a kind of optimization point of view. I would like to find the minimum of this function, and now I can try to have some kind of a comparison oracle, right? That tells me if A is better than B. So I will say that a candidate A beats the candidate B. Okay, so sorry. Just let me go back a little bit. So again, this is a median of means kind of estimator. So we start by partitioning the data into k blocks. All of them are equal size, and within each block we compute the average. Okay, so these averages, these y's are these points here. Okay, and now we say that A defeats B if A is closer. If A is closer to the majority of these block averages. Okay, so if the distance of A to yj is smaller than the distance of B to yj for at least half of the blocks. Okay, so this is kind of a median of means type of way of thinking about it. Okay, so now I have a way of comparing two candidates. Okay. And so here's a little statement that is the key to everything. What it says is that the true mean will defeat everybody, every other candidate that is more than distance r away, where r is exactly that sub-Gaussian quantity. Okay, now don't pay attention to these constants. They can probably be improved. We didn't really try. Okay. But you see, so what it says is that if I want to compare the true mean according to this criterion, the true mean to any other point, the true mean will be a winner unless that point is very close to the mean. Okay. Now, once I have this lemma, and I will show you a sketch of how to prove this. Now it's very easy to come up with an estimator, to cook up an estimator, because for each point, for each candidate point, I can look at the set of those points that defeat that point. Okay, so if I have a candidate estimator, I can look at the set. This is going to be a weird set. It's not convex or anything, but it's a bounded set, right? Because so if this is my point A, if I go far enough, then then eventually all the points will be on this side of this hyperplane. So A will beat that point. Okay, so if I look at the set of all those points that defeat A, that's gonna be some kind of a strange set, right? But it's a bounded set. Okay, and now I look at so the radius of a set is just the farthest point in the set from this center point A, and now I will choose A to be the point that minimizes the radius. Okay, that's our estimator. Okay, I warned you, this is not an algorithm. This is an existence proof. So this is just a measurable function of the data. Okay? These sets are well defined. So I can look through all these points, and I can choose the set that minimizes this radius. Okay. Now, of course, if mu hat n is my estimator, then of course the radius of the set corresponding to that is smaller than the radius of any other set, right? Because that's how we choose mu sub n. But because of the lemma that's on the previous slide, this radius is smaller than r. Okay? But then that means that, you know, here's mu n hat. Now, either mu beats mu n hat or mu n hat beats mu. Okay? So either mu is contained in this set, or mu n is contained in this set. But in both cases, their distance is smaller than r because the radius of both sets is smaller than r. So this distance is less than r. Okay, right? So by choosing by minimizing the radius of the set of the points that beat this candidate center A, we get an estimator that has the desired property. Okay. All right. So this is that remains to be proven. Okay, and let me show you very quickly just a quick sketch of how one can prove this. Okay, so what we need to know, what we need to prove, is that the true mean will defeat every other point. Of course, with probability 1 minus delta. Okay, the true mean will defeat every other point that's farther than this quantity. Okay. All right. So here's how the proof goes. So first we start by centering. Right? This doesn't make any difference. If you wish, we can just assume that mu equals 0. This is all translation invariant, so it doesn't matter. Okay. So now what we have to prove is that if you rewrite what that inequality means, that mu defeats b, then this is what you get. Okay, so what we have to prove is that on the majority of the blocks, the empirical average of the inner product of the data points with v are satisfy this inequality. Okay, and this should be true for all vectors v whose norm is at least r, but it's easy to see that it's sufficiently to prove that that this is true for all r's, because then everything else follows. Okay, so so we need to prove that that for every vector whose norm is r, so every vector on the ball of radius r, this inequality holds, right, with high probability on the majority of the blocks. Okay. Now, this is again a median of means type of proof. So first of all, let's look at a single v first, a single vector. Okay. So for a single vector, we can bound this quantity by Chebyshev's inequality. Okay, so this is trivial, and you see that this is with probability, let's say 90%. The magnitude of this is bounded by r squared divided by 2, but this guy here is r squared, so then this will be positive. Okay, so this happens with probability 9/10. So that means that this will happen on at least 80% of the blocks with probability that is exponentially large. The probability that it doesn't happen is exponentially small in the number of blocks k. Okay, so with probability at least 1 minus e to the minus k over 50, this inequality holds on the for 80% of the blocks for a single vector v. Okay. Good. But now, if this holds on for a single vector v on the sphere, then we can discretize the sphere, and we can take. I'm allowed to take, let's say, e to the k over 100 vectors on the sphere, and I can still use the union bound, right? Because this will still be this guy, and we will be simultaneously good for these exponentially many candidate vectors v. Okay, so that's what we do in the second step. We discretize, right? We have to discretize the sphere of radius r, with respect to this distance, right? So what we need to show, what we need to do is take a minimal epsilon cover in this distance, and I'm allowed to take epsilon so large that that we have this many points. Okay, and then using the so-called dual Sudakov's inequality, one can prove that that now this epsilon, the radius of this cover, is this quantity. Good, and now all we have to do is to control what happens. So now we know that this holds simultaneously for exponentially many candidate points. Now all we have to do is to look at what happens if for the fluctuations within each little ball. And I'm not going to go into that. This can be proven using standard empirical process techniques like Delagrange symmetrization and contraction, if there's anything. So I'm sure some of you know these techniques. Okay, so this is kind of standard stuff. So that's the proof. Now, as I said, computing this this estimator is a non-trivial affair. One can easily convert this into an algorithm that runs in time exponential in the dimension, but that's of course no good. So we posed in our paper this as a challenge to try to find a sub-Gaussian estimator that can be computed in time polynomially in the dimension. And then Sam Hopkins had a beautiful paper where he took this median of means tournament estimator. He managed to define a semi-definite relaxation of it, and he proved that that the estimator can be computed in polynomial time. Okay? This was the exponent of the polynomial was 8 in his paper, but this has been improved in subsequent papers. I mentioned 3 papers here, so now I'm not sure what the best exponent right now is. These are based on different ideas. Okay, so for example, gradient descent type of modifications of this and so on. Okay, so there's a whole world in the theoretical computer science community who care about algorithmic aspects of robust estimation, and this is one of the nice results there. Okay, so let me also tell you a little bit about a different estimator that's based on the median of means technique. Okay, so the trimmed mean. So the trimmed mean can also be generalized to high dimensions, and this is a very natural estimator. So what we do, just as before, we divide the data into 2 chunks. Okay, we use the second half of the data to compute empirical quantize, but now we do it on each one-dimensional projection. Okay, so for every point, every direction in the sphere, okay, continuum many, so lots of directions. We project. So on each direction we project, and now we just look at the empirical quantize, epsilon quantize on the left and on the right, and take the same estimator as before, right? That squishing function, right? So here you can see we project on this line, we compute this estimator. Oops. We compute the trim mean estimator on this. Okay. There's one little modification, is that here we have a parameter q, and so instead of looking at just these empirical epsilon quantize, we have to go a little bit beyond those. Okay, so we have to make it a little bit wider, and this is the price we have to pay so that these things work simultaneously in each direction. So this Q is some kind of a complexity parameter, right? So now once we have this, once we have this estimator, we define this slab, okay, which is defined here, and whose width is it also depends on the same Q. Okay, so this Q and this Q, that's the same value. Okay, so that's the width of this slab, and now we take all these slabs in each direction, and we take the the intersection of them. Okay, so in each direction we compute the trim mean. We look at these confidence bands, right? And we just see, we just take the intersection of those. Okay. And now how do we choose Q? Well, this can be chosen automatically because we can just choose the smallest value. Well, on this dyadic grid, we take the smallest value where this intersection is non-empty. Okay, when it still has at least one point, that's the value we take for it. Okay, our estimator is just an arbitrary point in this set. Right, so we narrow these things, right? We start with big fat slabs. If the set still has points, then we take half of it. We take half, and when it's empty, then we take one step back. We take that set and now take any point in that set. Okay, that's the multivariate trim mean estimator, and the main technical result is that if Q is of this form, okay, 1 over epsilon's root, you see the Frobenius norm, and this is the lambda one, sorry, this is the largest eigenvalue of the covariance matrix. So if we take Q of this form, then the corresponding set is not only not empty, but it also contains the true mean with probability 1 minus delta. Okay. And that's enough because these sets are nested, right? If I take now a smallest Q, so let's say for some value of Q, the true mean is there. Then if I take a smaller value, then the true mean is still there as long as this set is not.
Gabor, can I ask something?
Yeah.
I'm a little bit confused. You say that these sets are nested, but before you took an intersection of increasing Q, like what is going, like before you took an intersection overall.
I'm saying that, right? So this is for the same Q, right?
Yeah.
I take the same slabs of the same, right? And now if I take smaller slabs in all direction, then that will be contained in the previous.
But then why do you take the intersection over all I, at least I star? These are not like, it's just monotone the set?
Well, this is equivalent to saying that, sorry, I should have just written, this is gamma of 2 to the I star.
I see. Thank you.
Yeah. Okay, so you see that if we prove this, then because the diameter of this set is 4 epsilon q, right? It's the width, that's the width of these slabs, and it's in each direction. So the diameter is bounded by this. We have that any point in this set is at most this distance away from the true mean, and that's exactly of the form that we want. Okay. So I'm not going to say anything about the proof of this, but let me just say that this estimator is also robust against adversarial contamination, and you see, all we have to choose when eta times n data points can be contaminated, then all we have to do is to choose epsilon that depends on eta as well, exactly the same way as in the one-dimensional case. And then we have an error which has the sub-Gaussian term and the term that depends now here on the largest eigenvalue of the covariance matrix. So there's like the worst one-dimensional direction. So this is clearly necessary. Okay, and again we have the same kind of improvement if the distribution is sub-Gaussian when this square root of eta term can be replaced by something that's almost like eta. Okay, for sub-Gaussian distribution. And again, the proof is the proof that doesn't involve. I mean, yeah. So the proof is the same with contamination or without contamination. So this comes basically for free. Let me say that there's this very nice, very recent paper by Nicolas, Kane, and Pencia, who came up with a computational efficiently way of doing this, exactly this. So so it's an estimator, not based on trim means, as far as I understand, that has these two terms. So it's exactly the nice way, and it can be computed efficiently. So that's really nice. There are some intricacies here that I don't really understand yet. That if we want to improve this term here under tail conditions, that, for example, if we have improvements, sub-Gaussian, then the trim mean, the effect of the contamination is less, is lighter, okay, by the trim mean. Now, if you want to make this computationally efficient, this kind of improvement, then that seems to be computationally intractable. And Sam Hopkins and Jerry Lee have a paper where they give kind of complexity theoretic evidence for this. Okay. Okay. Is my time up? Let's say it is.
2-3 minutes.
Okay, let me finish here. Sorry?
2-3 minutes.
Let me finish here. That's okay. That's okay. I wanted to flash up some work in progress, but that's okay. That's for next time. So these are the references. The median of means tournament are in this paper. The trimmed mean for multivariate vectors is in this paper. There's another paper where we look at what happens if instead of the Euclidean distance, we care about some other norm. Okay, because in high dimensions, maybe it's not the Euclidean distance that one is interested in. You can think about trying to estimate means of random matrices, for example, or something else. So one can essentially characterize what's the best, what's kind of a sub-Gaussian analog that one can do. So that's in this paper, and we also wrote a survey on all this business, but it's getting outdated by the day. So I don't know, but maybe it's not too old yet. So that's all I want to say. Thank you.